Don't worry, Joseph. We will soon start. Once we start, you will hear everything. Nice you have connected, so don't worry about that, please. Don't worry, Joseph. We will soon start. Once we start, you will hear everything. Nice you have connected, so don't worry about it, please. Don't worry, Joseph. We will soon start. Once we start, you will hear everything. Nice you have connected, so don't worry about it, please. Good morning, class. I want to welcome you to today's 176 lecture. And we continue from where we stopped yesterday. You will recall that we were able to look at this particular chart yesterday, which showed us the oxidation trend in the preparation of carbonides. Our two groups of carbonides which we're studying are the aldehydes and the ketones. So we saw how from primary alcohol, oxidation continues first to aldehyde and ends on the formation of the carboxylic acid. For secondary alcohol, we have the oxidation ending with the ketone. And for a tertiary alcohol, because the carbon bonding to the OH, unlike the others that have one or two extra hydrogen bonded to it, that's why oxidation can continue. We don't have a carbon to hydrogen bond on the carbon that is bonded to a tertiary alcohol, that is carbon bonded to the OH of a tertiary alcohol, no hydrogen there. That is why what we're using to prove that a tertiary alcohol will not undergo oxidation. Yesterday too, I was able to tell you that we make use of chromium compounds in the process of oxidation, though a major disadvantage of these chromium compounds is that they are carcinogenic, they are dangerous to human health. But notwithstanding, just take cognizance that anytime you have I gave you this example first, where you have a secondary alcohol, butan 2-ol as an example, which in the presence of the chromium compound, so it's chromium trioxide here in acid, you have the ketone being formed, that's butanol. The cyclic alcohol, which happens to also be a secondary alcohol, also oxidized to cyclohexanol. Now, where you have this propanol as an example, let me quickly say that even though the first stage of the reaction is the formation of propanol from the propanol, but this reaction will not stop here if, because it's a primary alcohol we're starting with, and then if we reflux, that is, we add heat, it will not stop, it will proceed to propanol, formation of propanolic acid, which I'm not showing on this chart. May I quickly say that for any primary alcohol, if you don't reflux with the presence of the oxidizing agents, aldehyde may be collected, but in the presence of any refluxing, you will find out that the aldehyde that is formed will further oxidize to the carboxylic acids. This trend, the two trends, whether you are using a secondary alcohol to form the ketone or you are using a primary alcohol to form, we will soon see other examples with that now. Whether you are using a primary alcohol like this butanol to form in oxidation in the presence of these chromium compounds, you find out that this will end forming the acid. Let me quickly say that is the trend generally. We ended up giving this homework as an assignment yesterday, that you should try and show the products that will be obtained when you have the chromium compound, that's sodium chromate in tetraoxosulfate 6 dilute acid, reacting with each of these compounds. And like I highlighted before we went, that we should endeavor to recognize what type of alcohol are we working with. It is very straightforward once you know the type of alcohol. Now, this morning, we will be looking at preparing these two classes of carbonyls, utilizing a number of oxidizing agents. We'll be using not only the chromium compounds, we will also be utilizing some other oxidizing agents. I've labeled them here A to G. So please, as I pick them one by one, I want you to take cognizance of, at least recognize what is that oxidizing agent, the name and constituent, and are there some advantages or some importance of that oxidizing agent? Why are we using it? Does it have an advantage over the chromium compounds we are so used to that is utilized in oxidizing our carbonyls? So then first one is your chromium compounds, A, then anytime you make use of chromium compounds, generally our primary alcohols will oxidize first to the aldehyde, and in the presence of refluxing, you will see that the aldehyde that is formed will further oxidize to the carboxylic acid. And that is to show that all aldehydes are good reducing agents. So it shows that. Then, if it is still a ketone, you find out that, if it is a secondary alcohol, with this same chromium compound, you have the formation of your ketone finally. Let's check on another oxidizing agent, and that is utilizing, if you remember B, I said utilizing pyridinium chlorochromate. This reagent is shortened as PCC, representing pyridinium chlorochromate, PCC. You can call it where you are so that you are used to it. The PCC is utilized as oxidizing agent in this medium, dichloroethane. The major advantage here is what I've placed in red, that when you utilize PCC as our oxidizing agent, especially for a primary alcohol, it gives us the ability to stop the oxidation when we get the aldehyde. Peradventure, your interest is to get the aldehyde. Using the earlier chromium compound may not be easy to stop on formation of the aldehyde. But when you use this second reagent at B, PCC, in CH2Cl2, dichloromethane, it will oxidize the primary alcohol to aldehyde and the oxidation stops there. Of course, you still use that same reagent to oxidize our secondary alcohol to ketones. Let's see vivid examples in this perspective. for B. The oxidation of primary alcohol, such as our butanol, will stop at the formation of the aldehyde if we utilize PCC as our oxidizing agent in solvent like dichloromethane. I'm representing it with this equation here. And you are starting with butan 1-O, and you are ending with your aldehyde. And no further oxidation when you utilize this PCC CH2Cl2. It's a good selective oxidation reagent. The third one, C, is the Swine oxidation of alcohols. There are three major reagents that are involved here. We have the dimethyl sulfoxide, that's the CH3 of it bonded to SO, oxalyl chloride, which is a dimer compound of COCl2, that is COCl dimerized, and then triethylamine. These three combined together. Now, the advantage of this method, utilizing it in oxidizing alcohols, when our target is to obtain the carbonize, is that if you look at all the reagents, chromium is not a chromium-based reagent. Chromium compound is totally absent. And that's what it lessens its toxicity, which one will have experienced utilizing chromium compounds. So it's a better method that has been developed where chromium-based reagent is not utilized. Hence, it is less toxic. It's more human-friendly reaction. Now, the use of chromium-based reagents, we have said, is toxic. And so this method will be a development or a better method over the use of chromium-based reagents. Now, since the reagent too is not carried out in aqueous solution, there is nothing like water molecule in the reagents. The oxidation of a primary alcohol automatically stops when you form your aldehyde here too, just as we saw when we utilized PCC in B. And if you still use these oxidizing agents on secondary alcohols, you will obtain your ketones. It's still that's possible. Let's look at some equations that support this. So this is the three reagents utilized in Swan oxidation of alcohols. This is a primary alcohol here, propanol, and you are ending with propana. That's the aldehyde. So it's capable of obtaining your aldehyde when you make use of the Swan, the reagents for the Swan reagent, the three of them. Now, still for a secondary alcohol, like we said, the three constituents utilized, the three reagents, the three substances in the Swan oxidative reagent, will still result to give us the ketone. That's the normal thing that you are expecting. But at least the chromium-based compound that is more toxic is not handled here. So we have that. That's ABC. Now the D is going to show us how a 1,2-diol can be clipped, that is, can be broken, can be used in forming our carbonize with per-iodic acid. That is HiO4. That's our per-iodic acid. Over here in D, oxidative cleavage, we are making the cleavage on a 1,2-diol, that is neighboring, is not compulsory, it has to be on carbon number 1, but the diol must be such that they are near each other. Sorry, please. Let me pause for a moment and put it through. Like we were discussing, we said the oxidative cleavage utilizing this pyridic acid is on diols. The diols, that means there are two carbon OH bonds that are neighbors, that are near to each other. Look at my cursor here. That's why I call it a 1,2. Even though this very compound is 2-methyl, 2,3-butane diol. Yes. Yes, I've unmuted myself, please. Now, look at where my cursor is. They are neighboring carbons. So we have a COH bond and another COH bond neighboring. That's why I call it a 1,2 diol. Now, utilizing this reagent, per-iodic acid, HiO4, it's going to break in between. And the breakage, like I said, it will first form a kind of cyclic system like this. We will read what I have up here. But when the breakage occurs, depending on the structure of the carbon OH that we started with, if it is bonded to another hydrogen, like this, where my cursor is, this one, you know, this carbon OH has another hydrogen, though I didn't put it there. It's this part of the molecule, when it breaks here, we now yield an aldehyde, and that's the ethanol. A C, two hydrogen, two carbons. That is what is, this side is what is responsible for the ethanol here, the aldehyde. Whereas the other carbon here, the other all, C double bond OH, which makes it the diol. You will notice here that this very carbon is not carrying any hydrogen with it. There are two CH3s bonded directly to this carbon. So when the breakage occurs, this will not form an aldehyde, but a ketone. So, and that is what is responsible. This part of the molecule is what is responsible for forming the propanol, the ketone. So you recall that, let's just read through quickly, that 1,2 diols are obtained whenever you hydroxylate alkenes. I don't know, I feel you've treated alkenes, then alcohols too, which you will be taught. When the alkene is oxidized in that hydroxylation to a 1,2 diol, either utilizing potassium permanganate in cold basic solution or in OSO4, that is osmium tetroxide, to give the vicina diol, vicina or glycol, that is neighboring diols. The 1,2 diol are now oxidized to either form ketones or aldehydes or both of them. Like in this case, it's forming both of them. One molecule of aldehyde and one molecule of ketone, because of the structure we started with the presence of HiO4, the pyridic acid. I said the reaction occurs because iodine is in a highly positive oxidation state of +7. And that is why the reactions continue. The pyridic acid reacts with the diol to form first of all, a cyclic intermediate, and that is what you have here. So the intermediate is now what breaks or cleaves to form, that is, there is a cleavage here between the two carbons bonded to the oxygen breaks. Now, there are two Eves here, and that is what I've earlier explained, that when the carbon that is bonded to your OH, COH bond, is bonded to two other hydrocarbons, like here, CH3, CH3, that carbon carrying the OH is bonded to 2 other hydrocarbons. Then the final product will be a ketone, and that is what is responsible for this ketone propanone here. But if the carbon that is bonded, if the carbon of that OH, carbon to oxygen OH, is bonded to an R, an hydrocarbon CH3, and also an hydrogen, there is an hydrogen here that makes it 4, then the resulting products from here will be an aldehyde, and that is the SNR that is coming up from there. So please don't be confused at all. That is it. Though I'm better showing the same reaction in a larger form here. Another example, look at this cyclic diol. Of course, the diol is neighboring. That's why we still call it a 1,2. But you will notice that on this carbon, no hydrogen there. Whereas on this carbon carrying the OH, there is 1 hydrogen here. So this end of this molecule will be the aldehyde form. So that is what is responsible for this aldehyde form. Whereas the other end that does, where the COH bond, the carbon does not bond directly to an extra hydrogen, but to hydrocarbons. Then you have the ketonic end coming up from there. So that is just to show you the utilization of pyridic acid, HiO4, in formation of our carbonates. Let's go to another oxidation method that results to give us our carbonates. Here you are used to it. You've heard of ozonolysis before. In ozonolysis of unsaturated alkanes, that it helps us to locate where the unsaturation is on the alkane. It's an oxidative process, and where an ozonide is being formed during ozonolysis. It so much breaks that this part is a carbonyl compound. Depending on what are these 2 systems, 2 hydrocarbons or whatever, hydrogen that are bonded to that carbon-carbon double bond in order to determine the product. Let's see. Over here, immediately there was a double bond here before, and then on reacting with our ozone, it formed this ozonide. Now, the next step after the ozonide is formed depends on the reagent that is used in reacting with the ozonide. We can either have a reducing condition, like in this place, where we have zinc in water, utilizing CH3 dimethyl sulfide. Or we can have it hydrogen peroxide. It is an oxidizing condition. Hydrogen peroxide is the oxidizing condition, whereas zinc in water or this dimethyl sulfide is a reducing condition. The main difference, I'm going to read the slides out, or we go through the slides together, is that when you have a reducing condition, depending on the structure of what you started with, like over here now, this carbon here does not have any hydrogen, whereas this carbon here has hydrogen. The carbon that has hydrogen, just like my earlier instruction, after the break of the ozonide, you will have this one responsible for the aldehyde, and it stops there. That reaction, oxidative trend, stops there if you use reducing condition. Okay, when the carbon carrying hydrocarbons is on this side, that is no hydrogen bonded to it, it will, after breaking, you have, and under reducing condition, you have your ketone. But in the system, still the same structure of the ozonide. If you are making use of oxidizing condition of hydrogen peroxide, the aldehyde that will be formed from here will be further oxidized to the carboxylic acid. It won't stop at the aldehyde formation. And that is the main difference. So take cognizance, even in exam condition, that what kind of condition after ozonolysis, what condition is given? Is it reducing condition, or is it reducing condition, or is it oxidizing condition? So let's check on that. When the ozonide is clipped in presence of reducing agent like zinc or dimethyl sulfide, that's it here, then the product will be ketones, aldehydes, or both of them, like in this case, depending on the structure we started it. So, well, you can take cognizance of the things in red. Product will be ketone when the sp2 carbon of the alkene is bonded to 2 carbon-containing substituent. That is, that carbon does not bond directly to an hydrogen. And then product will be aldehyde if at least one of the substituent bonded to the sp2 carbon of the double bond is hydrogen, like here. So it will be an aldehyde. Now, the reducing agent prevents our aldehyde from being further oxidized to carboxylic acid when it is under reducing condition. So clipping your ozonide in the presence of zinc or dimethyl sulfide is referred to as you are working up that ozonolysis under reducing condition. Now, the other one at oxidizing condition. But if the ozonide that is being formed is clipped in presence of an oxidizing agent, like utilizing hydrogen peroxide, then the product will be the ketone and then carboxylic acid, or both, depending on the structure. What has happened? Actually, the carboxylic acid were formed instead of the aldehydes. And the reason is because the aldehyde that you initially formed will immediately oxidize further to carboxylic acid by that hydrogen peroxide. So take cognizance of what condition is following the ozonolysis, the ozonide formation. Anytime there is cleavage in the presence of hydrogen peroxide, you are saying that the working up of the ozonide is under oxidizing condition. So you will not observe aldehyde, but you will see that you will obtain carboxylic acid because of the further oxidation of the aldehyde to carboxylic acid. Now I want you to try this and determine what is happening. It's very, very straightforward. Very straightforward. What is happening to the person that is raising up hand? We need something. Please, once you come into the class, just come in and stop raising up your hand. So we have over here, we have ozonolysis, predict the ozonolysis product of, like the I now, the first one. You have a 3-methyl hex 3-ene under oxidized. What is H2O2? That's hydrogen peroxide. That's oxidizing condition at -17 degrees. The second one, ozonolysis of X3-ene, is utilizing dimethyl sulfide at -17 degrees, is under reducing condition. So if one of the carbon is still bonded to an hydrogen, then that means that it is under reducing condition. You observe an aldehyde, except it is not. The next one is zinc in water, which is still what we have talked about, that either zinc in water or dimethyl sulfide are referred to as reducing conditions. So for 1 pentene, you will find out, well, this is zinc in water. And what is that? That's a reducing condition. The other one is under oxidizing condition. I said 1 carbon fragment obtained from the reaction of a terminal alkene with ozone will be oxidized to methanol. That is this ones, that's IV and V, that's 4 and 5. If the ozonide is now worked up under reducing condition, it will now form methanoic acid. That is, if you have the aldehyde methana, that's the simplest aldehyde. Because we are carrying it up, if the ozonide is worked up under, you will have methana if the reaction is under, and you stop them, if it is under reducing condition. But if it is under oxidizing condition, then you will have that methana further oxidizing to methanoic acid. So there is no confusion at all about it. And that is what I've just given here for I to V that we have answered now. These are the answers. But adventure is supposed to be a home, it's a classwork. So, and that is why I'm giving you the answers straight off. Not to waste time. I guess you have the answers there. Let's try to see how we can synthesize or prepare our carbonides from dihalides. The position where dihalides, like you know, di means two. Two halogen bonded to the carbon in the molecule. Now, depending on the structure of the dihalides, are they on the same carbon, like in this one, 1,1-dichloroethane, or are they on different, carbons? Let me go back there, please. What I'm trying to say is that the dihalide, the carbon that is having that dihalide, is it at the extreme end, terminal, or is it in the middle? The first one I showed you here is a 1,1-dichloroethane. Well, 1,1, giving it the preference on carbon number 1, and more so it is terminal. But for this one here, which is a 2,2-dichloropropane on carbon number 2, which is not terminal, in between, you have this. When you have it as non-terminal, the dihalide on the same carbon, but that is in the middle, not terminal, then you are going to get a ketone. In this wise, because we are starting with 3 carbon system, prop, then we are ending with prop2, which is propanone ketone. So when they are not terminal, like I said, it gives our aldehyde. Let's go through this slide together. When there are 2 halogen atoms bonded to same carbon, please take note this as same carbon at end of the chain this time, as in this place now. After hydrolysis, the aldehyde is being formed. The mild alkali barium hydroxide may be used for hydrolysis. So we have that. Now, if you have the 2 halogens on a carbon in the middle of the chain, then a ketone will be formed, like I earlier showed you. Now, this is even supposed to be a classwork. I think it should be a classwork. Let's quickly do it. Can you show me the products of reacting barium hydroxide aqueous with each of 2,2-dichlorobutane this time, and then 1,1-dichloropropane. 1,1-dichloropropane is terminal, while 2,2-dichlorobutane is not terminal. And we have said for the non-terminal, should be able to form what? Thank you. I think you answered me. Should be able to form the ketone. While for the 1,1-dichloropropane, you should be able to form the aldehyde, and that is it. So here, the first one, the 2,2, which is non-terminal dichlorobutane, it forms the ketone butan. Whereas for the terminal 1,1-dichloropropane, it forms the propanol, the aldehyde. Now, we come to the reactions we have. Let's leave the preparations. We've done some good examples on the preparation of this carbonize. Let's check on the reactions of these carbonize, that is ketones and aldehydes. Let me say, don't run away. We have these examples to show us how the aldehydes and ketones that are examples of our carbonize, how they react. May I quickly say also that, let me mute. So like I said, I hope you've taken time to write some of them down. I have about 10, but don't worry, we may not treat everything in details. But those ones I touch, I want you to take cognizance because they have application in our practicals. That is Chemistry 191 practical class. You will be demonstrating some of the things I will be saying now on the reactions that are germane or distinguishing aldehydes and ketones from other compounds, and even differentiating them among themselves. Now, I'm sure you've been hearing about Tollin's reagents. In the Tollin's reagents, you have your diamine silver 1 complex causing the oxidation of aldehydes to give a visible silver mirror. And this is usually used to prove that a particular compound or substance is an aldehyde. We normally refer to it as our Tollin's test. What happens here is that the aldehyde, if it's an aldehyde, when it is mixed with Tollin's reagents in the tube, you will see a kind of mirror on the top test tube. That is why we refer to it as the silver mirror test for aldehydes. And what is basically happening here, the aldehyde we're using here as an example is ethanol. That should be the second member of the aldehyde. And then in the presence of your silver mirror, the Tollin's reagents, which is your diamine silver 1 complex, then you have in alkali medium, base medium, then you have the deposition of your silver, causing it to kind of mirroring pattern. That's why we call it a silver mirror. It's not a big deal there. The other reaction, the next one, is reacting our carbonate with derivatives of ammonia. And we have a number of compounds that is formed and which you also use in characterizing or detecting or proving that this is a carbonate. The addition of derivatives of ammonia, ammonia is NH3. So you have one of the NH bonds of the 3 now replaced by a Y. What is Y? In fact, that's a very good question you are asking. Y are a number of constituents. If your Y is an OH, then you refer to that derivative of ammonia as hydroxylamine. And that is what I'm giving you here. If that's Y happens to be an NH2, another NH2, you have an hydrazine. And then if the Y happens to be, that is, from this hydrazine, if one of the NH2 has one of the hydrogens replaced by a phenyl group, you call it, the diamino group, NH2 bonded, is hydrazine. So if one of the hydrogens in the 4 is just replaced by a phenyl group, you call it a phenyl hydrazine. And from that hydrazine too, if one of the 4 hydrogens is replaced by an amide, CONH derivative, then you call it a semicarbazide. After it had reacted with our carbonyl, these are the condensation product that results. If you are reacting it with derivative of ammonia, that is hydroxylamine, what you will form finally is the oxide, NOH bond. And then that's it. NOH bond is the hydroxylamine. And then the final product will be an oxide. Over here, it is hydrazone. For the phenylhydrazine reagents, you have phenylhydrazone. And then for the semicarbazide, it gives the condensed product called semicarbazole. So what happens is that, well, I've used Y to represent those varieties. See this as the carbonyl. Either you are seeing it as our ketone or aldehyde. Since it's a condensation reaction, we have the removal of water moiety. That is H2 from this, H2 and this oxygen here. They just condense. So we have water molecule being removed. So we have this carbon-nitrogen double bond, which after removal of water is coming up. Can you see? So irrespective of what A and G may be, you just remove the oxygen and then bond it to the nitrogen part of the derivative of the ammonia, and you have that. So the lone pair on nitrogen of ammonia and derivatives easily adds to carbonyl on aldehydes and ketones. Product that is formed is not very stable with ammonia, but with other derivatives of ammonia, which I've stated, I've shown you here, with all these derivatives, other derivatives of ammonia form useful products, the carbonyl. So such reaction are referred to as condensation reaction because you have a water molecule being removed. So, but that is the general equation. You can always form equation with specifics, specific reagents for each of them. Now, say for example, you have this benzaldehyde. It's an aromatic aldehyde. And you are reacting it straight with your phenylhydrazine. Here, you have this extreme H2 combined with the oxygen of the carbonyl of the benzaldehyde to give the phenylhydrazone. Let's see what is happening. That is, you have this H2 and O pulling out to form stable water molecule. So what is now left is that at this end, you have it joining here. So you have your phenylhydrazine. I think in the lab for your practical one, I will still demonstrate this too. So it's just a repetition of what I have up. That is what is down also. The products that we have seen is utilized in identification of aldehydes or ketones. You will recall that for qualitative detection of carbonyls, we make use of 2,4-dinitrophenylhydrazine. They are all derivatives of the phenylhydrazine, that is, of this hydrazine and phenylhydrazine that is there. So we have it in the lab. Is orange in color. When it reacts with our carbonyl, it results to give orange-yellow solid of 2,4-dinitrophenylhydrazone. And then, taking the melting point of such solid, you can easily prove that the hydrazone, the 2,4-dinitrophenylhydrazone, have been formed. The results can be used to characterize or identify our carbonyl. We surely do it in your practical 191. That's part of the practicals. Then another one is, our time is going systematically, but we still have some little more time. I think we can still move. Is the addition of cyanide to form, when you add cyanide, CN, to carbonyls, it results to give you your cyanohydrin. That is something like this. That's the general reaction for forming our cyanohydrin from any of the carbonyls, either it's a ketone or an aldehyde. Now, addition of cyanide to carbonyls gives the cyanohydrin. The method is used for making mixed acids and alcohols. Here, the alpha carbon to the nitrile group is with alcoholic OH in the cyanohydrin. That's it. So, as the alpha. Composition number 2, don't forget Greek word alpha. So, the cyanide group of the cyanohydrin is getting hydrolyzed to the corresponding carboxylic acid. And we will still need to touch this or just briefly mention it when we come to carboxylic acid. You will also notice that what you have started with has increased by an additional carbon in the final product. Here you have this. Now, after this one joins, and then you have additional, depending on what is this, the cyanide. So we have additional 1 carbon. All the time you have a cyanide reacting to form cyanohydrins. So that's one is it. A vivid example is reacting your cyanide with propanone under acid condition that activates it. You have your propanone cyanohydrin, which undergoes hydrolysis, water in acid, to give this compound. And that is where we're going. It forms, like I said, it gives the corresponding derivative of the carboxylic acid. And then, but let me just say here, because of this compound, which is important in the formation of our lactic acid, which we use in some of our drinks, yogurts specifically. So that is it being formed here. The 2 hydrox, okay. That is for this example, please. For this example. But before I go there, let me say that dehydration of this acid will result to give 2-methyl-propanoic acid, which is an unsaturated acid. Now, the next one is the one I'm trying to give as a reaction, and at the same time too, we are trying to see the importance of that reaction. For aldehydes, the one we checked on here is a ketone. Now for aldehydes, what happens? It forms the same protocol, the same thing occurs. For instance, we have your ethanol reacting with your cyanide to yield your 2-hydroxypropane. And in the presence of an acid, you have the 2-hydroxypropanoic acid being formed. The acid here is also called lactic acid, this one, which is the compound produced when our milk goes sour, as in the yogurt thing. The acid is industrially formed naturally by action of the bacteria Bacillus acidi lactic on sugars. So acid produced is utilized here in dyeings and leather industry. That's a very good importance for that product. For the aromatic aldehydes, we have tried to look at example with a ketone with an aldehyde, that is aliphatic ethanol, and now for the aromatic aldehyde, benzaldehyde. Of course, we react with the cyanide in presence of sodium hydrogen sulfide, and then you have your nitrite formed, which on hydrolysis gives the acid we are interested in. So, a few more minutes. I think we can still go, it's up to 10, but we see where we can stop. Yeah, I think I'm checking on the charts. Like I said, the link, the YouTube link, I'm also going to put on the charts. I've put it on the chat. You can still copy it and refer to that after the lecture. Now we have the fourth aspect of these reactions, and it's germane and good. Let's quickly brush through. We still have like 5 minutes or more. We have the reaction of carbonides with Grignard reagents. Like our Grignard reagents are alkyl magnesium halides, RMGX, shortened as GR. Now over here, the addition of our Grignard reagents to carbonyl compounds usually yield a new carbon-to-carbon bond formation. So this reaction yields a varieties of products depending on what is the structure of the carbonyl we're starting with and the structure of our Grignard reagents. May I quickly say that this equation below is showing us how the Grignard reagent is prepared in a dry system of diethyl ethanol with magnesium in your haloalkane. Example here, we are turning it to a Grignard reagent, starting with bromoethane, reacting in magnesium in dry diethyl ether. You have your ethyl magnesium bromide being formed therein. So you will recall that in Grignard reagents, the alkyl side is acting as a strong base because of the presence of kind of C- carbanion that is formed here, where you have my cursor. I said consequently also, aldehydes and ketones undergo nucleophilic addition reactions with GR, that is Grignard reagent. We talked so well about what nucleophilic addition reactions are yesterday, and that is what, like I said, is germane for the whole of this aspect of carbonyls, and that is what is happening here also. So the carbanion side, which is electron-rich, our nucleophile, is now the one that reacts with the C+, or so to say, the slightly electron deficient carbon in the carbonyl. I've told you about the polarity that occurs in the carbonyl bonding. So Grignard reagents will react with carbonyl carbon to form an alkoxide, first of all, that's the alkoxide for this particular starting material. And then with which complexes with magnesium ion. So an addition of water or dilute acid, you have that complex breaking up to the appropriate alcohol. So it resolves to give us the alcohol form of what we have started with. Now, look at this example of methanol. It's representing our carbonyl here, how it's reacting with a Grignard reagent. Look at the structure of your Grignard reagent and look at the final product after the formation of the alkoxide. You will see that there is an additional, the addition of the carbonyl here, because it's methanol, one single carbon, you have an additional carbon coming up there in the final product. It doesn't have to memorize, but you need to understand it. That is for the first member, the simplest member of the aldehydes, which is methanol. For methanol, it will form a primary alcohol. All the time methanol, the simplest aldehyde, reacts with any Grignard reagent, it will form a primary alcohol. But for other aldehydes, propanol, whatever, it will react with Grignard reagent to give or produce a secondary alcohol all the time. Later, please, later. 10 minutes. So for other aldehydes, like I said, it will react with Grignard reagent to produce a secondary alcohol. But if you have a ketone, the ketone will react with Grignard reagents to give a tertiary alcohol. Grignard reagent will react with ketones to give tertiary alcohols as our final product. Please take note of the three statements I've given. For methanol, it's going to give you a primary alcohol all the time, and that is with Grignard reagent. But for other aldehydes, it will give a secondary alcohol, while for ketones, it will react with Grignard reagent to give a tertiary alcohol. So many times this reaction is shortened by just writing 1 and 2. That is, first the formation, first the reaction of your carbonyl with the Grignard reagents, and then the hydrolysis that follows to yield the alcohol. I'm using a ketone to show this example. So in shorter form, not showing first formation of alkoxide, this and that, long equations. Numbers may just be used to indicate that there is a two-step reaction taking place in the order we have arranged it as 1 and 2. That is, your Grignard reagent will forcefully react with your carbonyl before the acid is being added to give your alcohol over there. So this is supposed to be a classwork, and I think I have the answers next, but I want you to copy it, and that is where we will stop this morning. I hope you have enjoyed the class. Thank you for not raising hands up and just registering yourself. Once you register yourself, I will see there. I'm putting again the link for the YouTube. I'm placing it there. So please, even the last person will still have it to refer to that. So please, let's have it that way. Now, 2 participants are raising up there.